Okay, good afternoon. Thanks everybody for joining in the Cruise Learning Lab 18. So I'm going to start sharing my screen and start the presentation. So for today, the Learning Lab 18, I'm going to be talking about a long short-term memory, or LSTM, as a machine learning algorithm for seismic inversion. So this is a solution that Sheng Huang and Paulina, okay, I forgot. Can you say your name, Paulina?
My name is Paulina Woźniakowska.
Okay, sorry about that. And they're going to show their solution for a competition in machine learning. So that's our guest is presented today. Sheng, would you like to present yourself?
Yeah, sure. Hi, everyone. My name is Shen Huang. I'm a PhD student at University of Calgary Cruise Group. And I have been working on multiple, migration with multiples. And I also have a part-time job. It's based on the sentiment analysis. That is the reason why I like to use long short-term memory in well-log dataset to have a good trail on those datasets. Yeah, that's me.
Oh, that's nice. Thanks a lot. Paulina, would you like now to present yourself?
I'm Paulina Woźniakowska. I'm doing PhD at the University of Calgary within Microseismic Industry Consortium. My research focus is induced seismicity and geospatial data analysis. And I'm doing also a little bit of machine learning within my PhD. Thank you.
She says a little bit, but both Sheng and Paulina, they're specialists in machine learning. So today for hosting, the session is going to be hosted by me. I'm Marcelo Guarido. So I'm a data scientist with a PhD in geophysics, and I'm at the head of the Cruise Data Science Initiative. And the co-hosts are Daniel Tread. Would you like to present yourself?
Yeah, I'm an associate professor at the University of Calgary, and I'm chairing exploration geophysics, and I just getting more and more into machine learning as the times demands, helping Marcelo with this data science initiative.
Thank you, Daniel. And also David Emery, would like to present yourself?
I'm David Emery. I've been volunteering with Cruise in the Data Science Initiative. I'm also the educational director for the CSEG for continuing education, and we'll be starting a PhD with Daniel in the fall in machine learning in seismic interpretation.
Thank you. Maybe I should already change here, right? To include that you are already a PhD student. You technically started. Okay, so now let's just present what is the Cruise Data Science Initiative. It's a subgroup inside the Cruise Consortium. That's a consortium at the University of Calgary related to the seismic acquisition, processing, and research. And for the Data Science Initiative, we are expanding our type of projects to the whole data science, geoscience, and engineering, mostly related to the energy sector. We work with academic and also industry projects. And we also offer some programming training, like in R, Python, and MATLAB that can be introductory training, as well as some applications in machine learning, and also how to create apps. And also we provide those learning labs. Those are the free webinars that we provide bi-weekly, where we show some research and some knowledge in our data science world related to the energy sector. So if you want, you can go to the Cruise website to learn more. So that's our website, www.cruise.org. So if you want to learn more about the data science, you go to the research and data science. And here you can also subscribe for our newsletter. We send the newsletters and also invitations for the next events by email, besides the LinkedIn account. And you can watch and have access to all the files and videos from the previous learning labs in here. And all the videos, they're actually in our YouTube channel. So if you wanted to stay tuned with our videos, so we have the learning labs, but there also be included more and more videos, short videos related to some tricks in Python, R, also other type of research. So if you want, just subscribe to our YouTube channel. So now going back to the presentation. Today, what Paulina and Shang are going to present is their solution for the Geophysics in the Cloud competition. So it was a competition that took place a couple months ago, and it was related to seismic inversion. The goal was to get seismic data, and using wall logs, you could train a model where you could invert for P and S impedances and density for the whole volume. They provided data for this competition. It was 3 seismic volumes. They had the near, mid, and far stacks, plus 1 velocity volume that was the stacking velocity, and also 6 wells with wireline logs that they used to complete the target, as well to use as the target. So the P-Impedance, S-Impedance, and density came from the wireline logs. The workflow for this competition, it was starting since the data acquisition, get the data in a AWS server. So that's why it's called the Geophysics in the Cloud. Everything should be done in a cloud system, suggested to be AWS. They had to do some analysis, check the data, understand what they had, and see what are the next steps they had to do for the research. And you're going to learn that any data science project is not only the modeling. Most of the part, we are working with cleaning, imputation, data augmentation, and all the pre-processing parts. So those 3 parts here take, also these 4 parts, also the analysis, take 80% of your data science project time. So they had to do some cleaning, removing spikes from the wall logs, data imputation, to recover the missing data for the DTC, DTS, and the RHOB. Those are the targets. They also worked to create some augmentation, create some data from the input data they had to help them in the modeling. And what they're going to be focusing today in the presentation is the modeling part, where they're going to use all the data that they cleaned before to do the modeling. And they're going to be focusing in the LSTM today. So now I'm going to pass to our guest presenters. So I think first is going to be Paulina sharing, right?
Yes, I will just
I'm
share
going
my
to stop sharing.
screen.
Okay, thank you.
Thanks, Marcelo, for this introduction. So our algorithm that we decided to use in this competition is a combination of CNNs and long short-term, so convolutional neural networks, as well as long short-term memory. So I will just very quickly go through the background and workflow, and then we will jump to the coding part. But in general, the problem that we had to answer within this competition, Marcelo already mentioned, but the goal was to perform the seismic inversion, but using the machine learning. So standard workflow, if you're not using those artificial intelligence methods, you're just taking the seismic as well as the well data and try to use the correlated well and extract the wavelet, and then build a model, I would say, by hand. And then you can perform the inversion to get the acoustic impedances and other parameters, rock properties. So that's the standard workflow. So basically you're having those seismic traces, and then you can just use the convolution to get the reflectivities. And then I will maybe just take my pointer. And then you can have either include your background velocity model or don't include it. And then from that, you can retrieve the acoustic impedances. So in this, just move it. In this competition, we just needed to find another solution for that. So we had multiple sparse well logs, as well as some horizons that were provided to us and seismic, and we had to predict those rock properties automatically. So this is the data set is located in the area of interest was located outside of Australia on the northwestern part. It was publicly available data set, and Marcelo already mentioned that it consisted on the mix of seismic as well as the well log data that was provided by the organizers. So this is just the quick look how it was looking for one of the wells that we were using. So we have this seismic data as well as velocity data and some well logs for this specific well. We can see that these are not complete. Like sometimes we had to perform some additional steps, some data imputation, for example, and I will just talk about that further. So first step of our workflow was the data pre-processing, specifically the feature engineering. So here we use the help from Kai. So it was another member of another team from Cruise that was working also within this hackathon. So he helped us to prepare those input parameters such as stacked seismic or intercept gradient, all this listed here. I will not go through the details. I know that he was explaining that in the previous meetings, but we can also provide more details if someone is more interested in that. So once our parameters were prepared, we also knew that sometimes we had to impute our data set. As you might remember in this previous slide that I shown, some well logs were missing. So we were trying to include some or use the iterative imputer from scikit-learn to try to retrieve those missing values. And we can see that it did fairly well job and it helped us to retrieve more data that was missing previously. So we were just starting to use the complete, like as complete as possible data that we had. So some other well logs that were complete in order to retrieve the missing well logs that were not available. And the next part, once we had our data prepared, we were constructing our model and train it. So here, I mentioned at the beginning that we were using CNNs as well as LSTMs for our project. So we were trying to combine those two methods. So I'm starting with convolutional neural network. So convolutional neural networks works in a way that they are most widely used for image processing or some feature detection from the images. And the main part of the convolutional neural network is this convolutional layer. And basically, those are within each convolution layer, we have our filters, which are used to detect some specific patterns between the data. So this is the main part of this network. So anything that is passed to this layer of convolutional layer, it gets transformed and it allows us to retrieve those hidden patterns, for example, edges or some circular spaces. So each convolutional layer that is deeper in the network is able to retrieve more and more complex features. Another element of the CNNs is the pooling layer, which helps us to downsample our dataset and create a layer that are smaller in terms of size, and also it just decreases the computational power. So you can see that CNNs are the mix of those layers. Those are the main ones. Sometimes you have some additional layers, but this is the main idea. You're just trying to convolute your inputs from previous layers in order to retrieve more and more features from your data. And one of the elements is also fully connected layers in which all neurons are interconnected with each other with the neurons from previous layer. And also another part of the algorithm that we were using, it was a long short-term memory model, and it's originated, or it's based on the idea of recurrent neural network. So in general example, when we have a recurrent neural network, we are just going in a sequence of the cells that are it's basically the passing of the information throughout the network. So recurrent LSTM neural network works similarly. So in general, LSTMs are widely used for time series forecasting or speech recognition, anything that has some patterns in our input data. And normally what distinguishes LSTMs from standard RNNs is the ability to estimate what kind of information should be passed to further into the network and which one should be ignored. And this is achieved by implementing so-called some specific gates, such as forget gates. That's the main part. Forget gate allows us to assess if the information provided by the input should be forgotten or should be passed further. And basically what the cell includes those forget gates, input gates, and output gates. And the main goal of the forget gate is to assign the value of this input from 0 to 1. So anything that is getting closer to 0 or is weighted as a 0, close to 0, it means that the network should forget this input, that it shouldn't be passed further within this cell state that it's called. Anything that it gets accepted and it gets assumed as important in the further steps, it goes to the input gate and then it's included into the network further. So this is the main goal, and I would say the main characteristic of this LSTM's neural network. It just allows us to remember only those information that are important for our model in the next steps. So here we decided to incorporate both of those, and we used CNNs because we wanted to extract the features from our dataset and our inputs that we inputted. And also we wanted to use this LSTM's element in order to predict it as a sequence, because we know that the data that we were providing in terms of the well logs, we know it's a continuous sequence. So we combined both of those to first extract the main features and then try to predict what is happening next. So basically that was a brief overview, and he wanted to acknowledge Data Science Initiative and CRU's team, as well as Marcelo, Daniel, David, Brian Russell, and John Dalton from CGG, who helped us to work on this algorithm and provided us with some guidance and ideas. And here are just some references that we used to prepare this presentation. And right now I will just pass over to Shang and she will explain the coding part. Thank you.
Thank you, Paulina. I will right now share my screen, and please let me know if you could see it. Could you see my screen right now?
Yeah, we can see it.
Awesome, great. So welcome to the coding part. Thanks, Paulina and Marcelo. Before we get started, we need to set up something like the runtime. If you also use Google Cloud Notebook, please choose like runtime to GPU because long short-term memory will use GPU, and click Save. Another thing is about the file directory. Because my data is stored in my Google Drive, so I need to mount the Google Drive here, or you could upload the data set just in the temporary directory. So next, I will introduce the package installation. We'll use Pandas, NumPy, Matplotlib, and for scalar, we'll use robust scalar from scikit-learn. And for the baseline model, we've tried the extreme gradient boosting regressor. And for the evaluation scores, we've used mean absolute score, R-square, and max error. For the models, because we've used two models, one is long short-term memory and the other one is convolutional neural network long short-term memory. So we need to set up the sequential layer, activation layer, dropout, dense, long short-term memory. And for convolutional neural network, we need conv 1D, max pooling 1D. And for this average pooling 1D, it is optional. If you would like to test, you could like import it here. For the evaluation score, the mean absolute error, which is defined by the sum of difference between observed and predicted, divided by the sum of observations. R-square is 1 minus the score, the value, which the denominator is TSS, the total sum of squares. The numerator, sorry, the numerator is sum of squares of residuals, and maximum residual is the maximum residual error. And the inversion, because our final target is P-Impedance and S-Impedance, which means A equals to the velocity times width density. But our target for training the model is P wave velocity, S wave velocity, and density. Next step is to load the data. So if you change the directory here to your own directory, you could load the data successfully. And here we could look at the features we have, like after Kai and looping's work, we could see there are 42 columns, which means like 42 features, shows like density, velocity, formation, near, mid, far, seismic offsites, background velocity, integral, absolute value, derivative value, some like instantaneous amplitude, instantaneous phase, frequencies, and so on. And next, I will plot the data with respect to density, P wave velocity, and S wave velocity. Like after imputation, the data seems like be continuous. And for next step, we need to figure out, like double check if our data set has non-value or not. Seems like there's no non-value, which is great. So next is to assign different well logs. And for this part, we need to filter the well data like with respect to different features. And you could choose some of them or remove them based on what you want about our features. Right now, I'm only like choose 37 features out of like 42, 43 features here. And next step is to do the train and testing data split. Because we only have few data sets, which is given by the organization. So we assigned the training wells as well number 1, well 11, well 21, well 25. And for the testing data set, we only use like well 27. And next step is to define the features and targets. Again, like the features, you could choose some of them or use all of them. Right now, I've used 37 features, and for target, we need to calculate the P wave velocity, S wave velocity, and density. Next step is to concat all of the training wells and drop rows with nonce. Because we don't have non-value, so I just comment out this code. But if you like need to double check, feel free to uncomment that. And next is to separate the data into inputs and targets. X train means like the inputs, which includes all of the data sets with features. And Y train means the targets, including VP, VS, and density. I will do like the same procedure for X test and Y test. Next is to scale the data. Like we've used robust scaler this time. You could choose like standard scaler if you want. And for the training or testing data set with features, we've only used like one scaler with respect to X string. And for the target, we develop like 3 different scalar, depends on VP, VS, and density. After we scale the data set, we need to convert them back to pandas data frame for following computation. And you could see it's an example of Y test after scaling with respect to VS. So next part is building the models. Our baseline model is extreme gradient boosting, and we use the regressor from the package. And here the parameter in estimators means the number of gradient boosted trees. Max depth is the maximum tree depth for base learners and jobs, which -1 means we used all of the course. And random state equals to 0. So next step is to fit the data set. The input should be scaled X train. And here the target, because we calculate the P wave first. So that is the scaled VP. And next do the prediction. So here's the thing that because we've used the scaled X test, after we calculate the prediction, we need to inverse that prediction to a normal true value. So at this time, we need to use inverse transform to transform the scale data set back to the true value. And here is the comparison between true training data sets and our predicted training data set. The blue line means true value and orange dashed line is the prediction. And here's the testing data comparison. So just remember that plot, hold on that. We will do the comparison with other models later. And here's the scores for our baseline model. And next, we will do the same procedure for VS, like train the model, predict the test data, do the inverse transform, and give the training data comparison. Here's the testing data. We could say like the baseline model gives more blocky values for VS. And here's the evaluation scores. And next is the density part. Sorry, here's the directory, you could see like which part we are going. We've used the same model and then following with inverse transform, train data sets, and have our testing data with respect to density. It's very tricky that we cannot recover very well for later part, like after 3200 milliseconds data set. Some reasons could be generating that. One could be the insufficient data set because we only have few well logs. The other one could be like the density is not very relevant to other parameters. And here's the scores. Next, we need to compute the impedance because our final target is impedance. For testing data, it's equal to the p-wave velocity times with density times with 1000. Here 1000 due to the unit transform. And we done the same for the prediction data. And here is the comparison. And this is the R2 score. And we'll do the same for the S-Impedance. Okay, so next we will do our first model, long short-term memory. So we need to reshape our input data set because for the input layer of long short-term memory, it includes 3 dimensions, like samples, time steps, and features. For samples, for example, like we see here after reshaping, we have 2776 samples. And for the time steps, which is 1 here, if you want your network have memory of like 30 or 60 time series points, you could change it to 30 or 60. And features here, we've used like 37. After reshaping the data sets, and we define the callbacks like patient as 3. And then we build our long short-term memory model, start from the sequential layer, following with long short-term memory. And the recurrent dropout we define as 0.2, which is the regularization method for recurring neural networks. And the return sequences equals to true, which was true because it needs like full sequences of hidden states. If it is false, we only have the final output hidden states. And dropout is 0.2, following with output layer dense. And for the training, we set the iteration at 30. If you have more time to train your model, you could choose say like 50 or 100. And the validation split is 0.2, following with evaluation process. And here is the summary of our model. The same, like after we predicted the data set, we need to use inverse transform to back to the true value. And training data sets looks like the amplitude is close to the true value compared with our baseline model. Like the peaks and troughs are well followed. And here's the results for testing and the scores. Now we could compare our model 1 with our baseline model. Well, like the blue line is the true VP and red line is predicted by gradient boosting regressor, and orange dashed line is long short-term memory result. So you could see like the shallow part, the long short-term memory could follow the trend well, except for some spikes, as well as for around 3,000 milliseconds, some peaks and details are performed very well for the long short-term memory. But here's like side effects for the spikes. One potential solution could be using median filter, and the other one is to increase the states. Like you could change this number like here, larger. I choose 256 because when I tried 128 and 1024, I found only like 256 is good enough for giving a better result. And next, the same, we need to predict the VS. Following the same procedure, do the inverse transform. Here's the training data comparison, testing data, which looks better, I believe, for VS compared with VP, but still it has some spikes at the beginning and the deeper seconds. And here's the comparison between our baseline model and model 1, long short-term memory. So we could see like, especially like 3,000 milliseconds, it could derive some like formation change compared with gradient boosting regressor. And for density, we use the XM model to train it. After 30 iterations, do the inverse transform. Here's the training data for density. And here's the testing, which is quite weird that we could see like a big drop after 3,200 milliseconds. But before that line, everything looks fine and add more details. So the same, like probably we don't have sufficient data sets, or the density needs more constraints to calculate or predict. And here's the scores. And the comparison for before the 3,200 milliseconds, I would say long short-term memory could catch more details, but after that, gradient boosting regressor has a better job. For impedance comparison, P-Impedance, here's the figure. And for the long short-term memory, it follows quite well at the beginning, except for the spike, the same, as well as here and also here. And here's the R² score. And for S-Impedance, quite similar trend compared with P-Impedance. And next, I will introduce the convolutional neural network and long short-term memory. We look forward to seeing like a better results after using this one. So the input shape for this model, it also includes like 3 dimensions, number of examples, time steps, and features. So before introduce the model itself, the convolutional layer, like Paulina said just now, is a layer that consists of a set of filters. And pooling layer, it's replace each patch in the input with a single output, like maximum we've used in this model. And dense layer, also known as fully connected layer, it's a linear operation where every input is connected to every output by a weight. So for building the model, sequential at the beginning, following with like 3 comp 1D layer here. We define 3 comp 1D because it's quite similar. The function is quite similar to feature engineering, that it is doing the cross correlation with features and then extract some information from the features to have a stabilizing factor. We'll see the result later, like about the stabilization. And following with a long short-term memory model, output layer is still the dense layer. And we calculate the p-wave velocity first. And here is the model structure. We have like many parameters here. And then do the inverse transform after prediction. And here's the training data comparison, testing data. Oh, looks great. Like we don't have any like high spikes or unexpected spikes at the beginning and the end. It's just good. And this is a score for the model 2. If we do the comparison, we could see like the model 2 is more stable, removing some artifacts, also have a good fit, align the true p-wave velocity compared with gradient boosting. And next is to do the shear wave velocity. Here's the training data, testing data, which is like better than the p-wave velocity. And if we do the comparison with the model, baseline model, you can see like except for the middle parts, like 2800 milliseconds, I would say both shallow part and deeper parts could derive the correct trend of the true values and gives more details about our well-logged data. For the density parts, here's the training and testing. I would say it's better than the model 1, which is only using long short-term memory, but still you could see like a big drop at after 3200 milliseconds. And here's a comparison between baseline and our model 2. For impedance, here is the p-wave impedance. You could see like quite similar to the p-wave velocity, but for some details like here, the trough, it could be predicting very well, and also like the beginning parts compare with the other baseline model, also like the middle parts. And here's the R-square score. And this plot is for S-Impedance. I really love this part. Like it could predict very well for the trough. And for summary, if we look at the p-wave velocity, like 3 models, baseline, model 1, model 2, for R-square score, the model 2 could give a higher score compared with other 2. But for the first and the third score, I would say like baseline could be more like moderate model compared with the other. And here's the figure showing 3 different models. Like the blue line is true value, red line is gradient boosting, orange dashed line is long short-term memory, and green star line is convolutional neural network plus long short-term memory. So the green line is way better than the other two for this plot because it can like follow the trend variable and remove some spike as well, except for this middle parts. So next step we'll work on to like how to remove some like high bias, but for the other part it like follows pretty good. And for VS, still like our model 2 has the highest score for R square. And here's the plot. Like green line by the model 2 gives more details, and which is close enough to the true values. And for density, which is sad that our model cannot have a better job compared to other like baseline model, but this is fine. Like R squared doesn't mean like your predicted data is bad or good. It's just a reference. And here's the results. I would say like before 3200 milliseconds is pretty nice, but after that some like unexpected troughs happen. And here I will show the R square for impedance, like our final target. So here is the P-Impedance, like green line, which is model 2, gives the best result compared with the other two models. And S-Impedance, which is more close to the true value, except for the shallow parts. For the middle one, it is not as good as our first model, but for the later parts, it derives a good value for the testing. And here's the R square for impedance. Like our model 2 has a higher score for S-Impedance, but not a higher score for P-Impedance. An option to increase the R square or the results is to use the median filter. Here I choose the parameter as 20. And then after use the median filter, you can see like the result is pretty much close to the true value and better than other two methods. And for S-Impedance, the same. This is really nice. And here's the R square. We could see like both P-Impedance and S-Impedance R square is larger than baseline. But again, like if you have a higher or lower R square, it doesn't mean like your value is good or bad. It depends on the interpretation and your testing data and the real trend. And reference is the definition of dense layer, convolutional layer, and the fully connected layer. So that is my part. Thanks for listening. And any questions?
Sean, I don't know if you explained it or if you did, you went a bit too fast. I don't remember if you did. The reason why you are using the LSTM or in general any recurrent neural network. So you have a time direction, right? So you're basically doing some assumptions about how the points are connected. Do you want to try to explain that part?
Good point. Thanks, Daniel. That because I've used long short-term memory for sentiment analysis, but I found long short-term memory could be also used in time series. And for well-log data, it is also with respect to like two-way travel time. So I was just wondering if we could use long short-term memory for well-log data for inversion. So I started to begin the trail. Yeah, that is my motivation to do the long short-term memory. For the time dependencies, I would say it's very tricky because different depend on the different background or the reservoir background. It is hard to tell if the well-logged datasets really have the time dependencies. So I just set the time step as 1. Like for other methods, predicting other time series, you could like find the pattern or the trend. So you could see the time steps equals to 32, 64, or even larger. But for our geophysics data, I like only set like 1 because I don't want to put our well log to depend on our like time. So I just set 1.
Okay, there was a question here on the chat by Brian Wang. I replied him, but he was asking if he did use the scikit-learn imputer somewhere, the interactive imputer.
Yeah, it's from Kai and Looping's workshop, I believe, mainly in Looping's workshop for imputation. So
Yeah.
in our workshop, yeah. Sorry, go ahead.
No, sorry.
Yeah, like in our workshop, we only used their pre-processed data set as our input for mainly deriving the models, the training process. Yeah, sure. Marcelo, could you please like share the Cruise Data Science website or any links?
Sure. So the
Thanks.
link is going to be in the Cruise data site, www.cruise.org. And there you just go to the research link and data science, and you can find all the files and presentations from the previous webinars. So I think you are talking about the lab 15 that was looping. She actually did that in MATLAB, all the data imputation, but we also used the lab 15, correct? But we also used the interactive imputer.
Yeah, and Paulina, feel free to jump in to correct me if I like answer some wrong points.
No, like you're right. Like we were for this workshop, we had already prepared the data set, so it was pre-processed. But we were also trying to include this iterative imputer, and it was working well. Even I was trying to, for example, impute VP values based on only VS based on only VP values, and it was working fairly well. Like we were able to retrain that. So yeah, we just didn't show it there. But it was fairly easy also to incorporate that from the scikit-learn package.
Yeah.
And just a reminder for everyone that's attending. So this lab today, the lab 18, is the 4th and the last lab related to this competition. So it started on the lab 15 with this data imputation, lab 16 with the data preparation and feature engineering. Lab 17 was using convolutional neural networks or UNet model for the predictions, and today is using the LSTM. So there is a question from Brian. Did you guys consider any smoothing for CNN?
Good point. So far for our CNN, we only use like as simple as we could. I would say we only use like max pooling for extract some key information from the features. But other smoothing, we didn't include that in this workshop. But we could try it like after then. And one filter I said just now is like a medium filter, but it's after using the convolutional neural network and long short-term memory.
Okay.
Yep.
So do you have
Thanks
any
for
other
asking.
questions? Oh. Do you have more questions? If you have questions, you can unmute yourself and ask, or you can type here in the chat.
Thank you, Brian.
Okay, if you're done, then I can share my screen just to finish today's learning
Yeah,
lab.
sure.
So I just like to announce that the next learning lab is going to be July 8th. So you're going to have another guest presenter, Ryan Mardani, and he's going to be presenting about neural networks from scratch in Python with geoscience examples. So he's going to be teaching step by step how to build these different type of models. And if you're interested to follow us on our social media, we have a YouTube channel, Twitter, and LinkedIn group. So I'd like to thank everybody for joining today. And I guess that's it. I'm just gonna. And thank you for everybody for joining, and see you in 2 weeks.